240. Okay, it's time. Any questions? Yes. Which lecture slide? Oh, they're not uploaded? Oh my goodness. Okay. All right, I will do that right now. Because they're there. I didn't upload them. All right, they're there. Okay, we're back. Other questions? Yes?
I don't see where to submit homework to.
You don't. Oh. Uh-oh. Okay. How about there? Is that the right date? I think that's the right date, yes. Okay, anything else I need to fix? Yes.
Nothing, for the homework 2 problem 4, that was the code, are we covering that too?
What do you mean covering that?
There was one of the problems that you said we would, like, the...
Number 5 we'll cover.
Oh, number 5.
Yeah. Number 4 you should be able to do.
Okay.
This is, just very basic Verilog instantiation of module, passing arguments. I do want to point out that this is the proper way to do a Boolean AND. Okay? It is easy to do that instead. And this happens to work if A and B are 1-bit vectors. But if they are not 1-bit vectors, this is not what you want, because the two vectors are treated as numbers and then they're multiplied. So if you have two vectors that represent 2 and you AND them, you want to AND them, you'll get 2, right? But if you put a star there, you're going to get 4. Yes?
Are we supposed to, when you say expressions, do you mean Boolean algebra or do you mean Verilog?
In Verilog. So in Verilog, if you write A star, if I do assign x equal to this and assign y equal to that, it'll look different on a schematic. It will happen to give you the correct value if A and B, or the circuit will give you the correct value if A and B are 1-bit vectors, but not if they're bigger vectors.
I meant in terms of like when it's asking for minimal expressions.
Oh, so you can write out your minimal expressions in Boolean fashion.
Oh, okay.
That's fine. Don't have to use ampersand or star. So this is something that I've noticed, because when you're doing single wires, you get away with it. It works. But when you go higher, it won't work. there's also a third one that I see a lot, and I think it's because you've been taught C, and this also happens to work with 1-bit vectors, but not with higher, because this is a logical AND, not a Boolean. Basically, unless A is 0, and if A is 0 and B is 0, then you'll get 0. But it won't work. You'll get the result of this will be 1 if A is some vector that isn't 0 and B is some vector that isn't 0. It's not going to be the bitwise AND of A and B. It's just going to be 1, a single bit of 1. Okay, so don't do that. Okay, if you're writing logic equations, you want to use the ampersand. If you're writing the OR, you want to use the vertical bar. Okay, this is one where you won't get away with the plus. Okay, because if we do, what happens if you have 1 quote B1 plus 1 quote B1? What do you think you get? Yes.
0 and it overflows?
Yes, you get 2 quote B10. You get a 2-bit number, but if you're stuffing it into 1 bit, it's just going to save the 0 for you. Okay, so no. Okay, one vertical bar for the same reason. Okay, just trying to save you a lot of grief. So our designs are going to get more and more complicated, and attention to detail will save you a lot of time and a lot of grief. Okay, tracking down those little tiny things that don't work takes a lot of time to figure it out. So be very deliberate, careful. It isn't all that intellectually hard what you're doing, but it requires an attention to detail. Having the mindset of an accountant is a big plus in this course. It'll really save you time. Okay, if you go in and look at the assignment, your goal is to just try to get done as quickly as possible and read as little as possible to get it done. It's going to backfire. You're going to take even more time. Okay, any other questions? Okay, homework 2 is due Wednesday night, and then we'll have homework 3. Let's see where we are. Okay, today we're going to talk about counters for the first time. Okay, so in lab 3 is due next Tuesday. You're going to need to simulate as part of lab 3, and you're going to be making your own test benches from now on. Okay, all right. Any other questions? No? We'll get rid of this. It's distracting. All right, so let's pick up sort of where we left off, or maybe we'll do a brief recap. Okay, so last time we started talking about combinational versus sequential circuits, right? And for sequential circuits, we are going to have to remember something about the past. And to remember the past, we are going to use the D flip-flop. And this is how we instantiate a D flip-flop. They are already present on the FPGA. It's just a matter of using them, connecting them up so that they are part of your circuit. Okay, we looked at how the D flip-flop behaved. The D flip-flop will load whatever's on the D input at the rising edge of the clock. These flip-flops only react to the rising edge, not the falling edge. So whatever value is on the D input, that's the value the output will take on a little bit after the clock edge. Not immediately at the clock edge, but a little after. If this is the very first clock edge, and you haven't been told that the flip-flops were initialized, then you don't know what they were. You don't know what value this flip-flop has before the first clock edge, and so you should mark it as unknown. Okay, so in this case, x was 0, so y became 0, and it'll stay that way regardless of what happens with x. X can change all it wants. It's only the value of x at the clock edge that matters. There is a warning, a caveat, and that is in order for the D flip-flop to work properly, the input x has to be stable right around the clock edge. If you change x right at the clock edge, havoc may ensue. It's not just a matter of not getting the value on time. I mean, you would pick it up on the next clock edge. You can actually cause the flip-flop to oscillate. Okay, so we went over the commandments for synchronous design. Yeah?
On the topic of D needing to be stable when the flip-flop is reading, is that going to be a problem for lab 3? Because I'm thinking we're feeding things like button inputs into D.
Good question. Yes, it might be. We'll talk about that.
Okay. Thank you.
Yeah, I mean, if you have an input that's coming from outside your circuit, and that's not sharing a clock, right? We don't wire you guys up to the clock in the lab, so you can push the button at any time you like. You might push a button right at the clock edge. It would be extremely hard to plan this, but if you get close enough, yes, it could be a problem. All right. So we did a 3-bit shift register, right? And this, basically we can hook up 3 flip-flops in series. The output of one is the input of the next one. They all have the same clock because that's one of our commandments. And then we looked at that. And then we did the parity checker really quick. And for the parity checker, we realized that we didn't need to remember all the past inputs. We just needed to remember what the parity of the past inputs were. And so that's our state here. We can figure out what our current output is by knowing what our current input is and what the parity was before. And so that led to this little circuit. And so here's our output. And we're actually feeding it back so at the clock edge, it will be loaded and become the past in the future. Yes?
Out of curiosity, what do we use parity checkers for?
Well, when you want to alternate something, so you want to flash something, you can just feed a 1 there. They're part of parity comes up a lot in error correcting codes. And also, I mean, the XOR is almost everywhere in arithmetic circuits. Yes?
I noticed there's a lot of arguments, like more than I see like connected to this module here in the actual like declaration in Verilog. Are we mostly just going to keep the like reset always off and then the like CE always on?
Where'd it go? Where's my default? Okay, so this is the full declaration of a flip-flop with a reset and enable. don't necessarily need to use the reset. There may be some future circuits where it's useful for you to use it. The clock enable you could use or not use. And when you have a register and you want to hold a value, you don't want it loaded every clock, only when you tell it to load. That's when you're going to use the clock enable. Now, these pins should appear in the instantiation whether you want to use them or not. If you leave them out, you're telling Vivado, hey, I don't care, you choose. And it might choose the right value. You obviously don't want it to put a 1 in the reset, because then that flip-flop will always output a 0, which is not helpful. And you don't want it to put a 0 in the clock enable, because then that flip-flop will never load anything. Okay? I have seen it do that. So please specify them, even if you need to put a constant value in the inputs. You do not put constant values in the outputs. If you have an output you don't want to use, just leave it unconnected. Okay, if you actually put a constant into an output, what you're doing is you're driving that net with the module and your constant, and you'll get a multi-source net error. Okay, outputs you can just ignore if you don't want them. Inputs you should specify, or you're leaving it to Vivado. Now, this leads to kind of a strange simulation, where if you simulate, you get all these unknowns in your simulation, but your circuit works just fine on the board. And what happened is, of course, you got lucky. Vivado put zeros there, and you wanted zeros there. Okay, it worked out. But when you simulate, you don't get any information, because the simulator won't do that for you. The simulator will say, hey, it's unknown. You didn't specify it, so I don't know. And I'm going to mark it as unknown. And then everything becomes unknown, and you've got a sea of red. And then you have to go plug in values and fix it. But anyway, okay. Let's go back on it. So where were we? Okay. So this is, our state, basically what we're remembering is the past parity. Okay. For parity, it's very important that we start at 0. If the initial state isn't 0, we'll never get the right answer. Right? So if we haven't started, that means we haven't seen any ones yet, and our parity should be 0 at the beginning. And so we may need to implement a reset. On the FPGA, this is there for you. You don't have to make it yourself. If you do want to use the reset as part of your design, you can. You can feed a signal to here. But if you only want it to reset when you download, you don't need to do anything. All the flip-flops will be reset to 0 for you. If you want to reset the whole design, you can use a global reset. This is a built-in signal on the FPGA that zaps all the flip-flops, forces them to 0. In Lab 2, we connected button R to the global reset. And you will be given a clock module for every lab, and it'll ask you to connect a button to the reset. And what you're doing is you're taking advantage of the global reset. When you push that button, all your flip-flops will be reset. Okay. And you can configure individual flip-flops to be 1 on a global reset rather than 0 if you want. Okay, so then we simulated the parity checker, and it worked. Okay, and we talked about the clock enable and how this is not how we implement a clock enable. You never, ever want to do any logic on the clock. Instead, what the clock enable does is it selects whether you're going to load the new value or recycle the old one. So when the enable is low, we're just feeding back the same old thing. And so it won't change. When the enable is high, then we allow the new value to go through. Of course, this only loads on the clock edge. Yes?
So if we can only like hook up the clock to the clock enable, that's like the golden rule in the lab, I know. How are we supposed, like, what if my user like hits a button to like load a new value onto my adder, but the clock happens to be like on the low cycle at the exact moment?
You know, your clocks are going to be so fast that you're not going to notice.
Oh, okay. It's like superhuman. I get you.
Yeah, you won't know.
But so you're telling me there's a chance.
You won't notice which clock cycle you hit, okay? I mean, the slowest clocks that you're going to have are going to be less, in the kilohertz.
Oh, okay.
And the only reason I'm giving you a slow clock is so that you don't have to deal with the bouncing.
Thank you.
Yeah, I appreciate that.
Okay. Sometimes you want your flip-flop to wake up with a 1 or go to 1, and we talked about that. Okay. And the caveat is that using the parameter, this only affects the global reset. If you use the R pin of the flip-flop, it will not cause this flip-flop to go to 1, even though you have set the init to 1. So the init to 1 is only for the global reset, or the initial download. Okay, all right. Okay, all right, so let's talk about 4-bit counter. So you're building a 5-bit counter, and then a 15-bit counter, but I'm going to do this with 4 bits, so it fits on my slide better. So a standard 4-bit binary counter, plain old vanilla, would have just the clock as input and a control to increment, or we could call this count enable, if you like, also. It always goes up, so we don't have to worry about whether it's going up or down. This only goes up. It has 4 bits, a bit vector, if you like, that represents a value. And basically, at the clock edge, if increment is high, it advances to the next value. You would likely want your counter to start at 0. And on an FPGA, that's what's going to happen, so you don't have to worry about it. And so when increment is high, on a clock edge, it'll go to 1. And then if the increment is low, it'll stay there. And then if increment goes high again on a later clock edge, it'll go to 2 and 3, all the way up to 15. And then if increment is high again on a clock edge, it'll go to 0. So it can only hold 16 values. It has 4 bits and 16 states. The highest value, 15, causes the terminal count output to go high. So this is an indication, hey, I'm at my highest value. If you count again, I'm going to go roll over and go back to 0. Okay, and if you're interested, this might be important, particularly if you're building a bigger counter or you need to know when you hit 15. Okay, because if you count one more time, you're going to forget. You're going to go all the way back to 0. So this is called terminal count. Okay, so how do we build a 4-bit counter? Well, let's look at the pattern that you see in a 4-bit counter. So here we're starting at 0, and then we're going through the progression of the different values. These are all binary values. And you will see that bit 0 always changes when you increment. Right? Makes sense. You go from odd to even, you go odd, even, odd, even, odd, even. What about the next bit? In order for the next bit to be 1, we need bit 0 to be 1. Okay, so whenever bit 0 is 1 and we increment, bit 1 will go from 0 to 1, or it'll go from 1 to 0. Because there's been a carry into that position. And then this repeats. Bit 2 will change when both bit 1 and bit 0 are 1. Because if adding 1 causes a carry into that position. So bit 2, over here it'll go back to 0 again when bit 1 and bit 0 are all 1. And if you look at bit 3 changes when you're at 7. And when you're at 15. And this occurs when bit 2, bit 1, and bit 0 are 1. All three of them. Okay. So this is the pattern you see. And we can use it to generate the logic. This is, again, the pattern of the counter. You can see bit 0 changing every clock cycle. We're holding the increment high here. Right? If I bring it low, then this will pause. It'll stop changing. Okay? Bit 1 changes whenever bit 0 is 1. Here, yes?
In lab 3, like to make the down counter as well as the up counter, would I be allowed to just like invert the output of the up counter?
No. That won't work.
Oh man.
Sorry.
The first cycle would be 1 1 1 1, then it would go to
We'll talk about the down counter. Sorry. Okay, so you can see that each one of these bits is oscillating, but at different rates, at half the speed of the previous bit. Okay, and it only changes when all of the previous bits are 1. Okay, so if we were to try in general to come up with an equation for, say, bit I, we would ask ourselves, when does bit I change? Bit I changes only when all the bits to its right are 1. So in order for bit I to change, we need all of the bits to the left to be 1. Okay, and that even for it to go from 1 to 0. If it's 0 currently, in order for it to go back to 0, we again need a carry. So we can write an equation for this. Bit I will change, so this is an XOR, right? If you XOR with a 1, you're basically inverting BI. So when do we want BI to change? Well, inc has to be 1, and all the bits to the left have to be 1, to the right have to be 1. So there's your logic equation for the next value of BI. BI will flip, it'll go from 1 to 0 or 0 to 1 if this AND is 1. Yes?
So, for the purposes of lab 3, should we do it this way, or can we be lazy and use our adder from lab 2?
You should do it this way.
All right. Just to learn?
Yeah, you need a subtractor, right, too, and it gets complicated. You need a bunch of things if you do it the other way.
You had us make a subtractor.
Darn it. And so it's good to understand how the counters actually work.
Yes.
Okay. So the counter determines the speed at which your processor can run. What is at the heart of a microprocessor? the program counter, right? If you can't run instructions faster than your program counter can increment. Okay, so making fast counters is really important. And maybe it didn't matter when we had 8-bit instructions, but hey, we have 64-bit instructions now. Okay. And who knows what the future will bring. Okay. All right. Okay, so that's what it looks like if we do this. Right? We have a flip-flop holding each of the 4 bits. And the next value for each of these is basically the XOR of the current value. For B0, we just need to know whether it's supposed to count or not. So if we don't count, it'll just be B0, and if we do count, it'll invert. For B1, we will advance only if B0 is 1 and we are told to count. For B2, we need the AND of INC and the previous 2 bits. And for B3, we need an AND of 3 bits, 3 of the previous bits with the INC. So you can see these very regular structure here, and we could keep going. Right? You could easily add a 5th flip-flop and a 5-input AND gate to get your 5th bit. Right? Okay. And the TC here, remember the TC is just high when all the bits are 1. So an AND gate does that for us. So this is the 4-bit counter. In general, the input equation for the flip-flop that's holding bit I is just bit I XORed with INC ANDed with all the previous bits. Okay, so if I keep doing this, how big is this AND gate getting? Too large, right? If I wanted to make a 64-bit counter, I'd have to have a 64-bit AND gate for the last bit. So this isn't very practical. An alternative is taking advantage of the fact that this AND gate is actually ANDing some of the same bits as the previous AND gate. So instead of doing this from scratch, I could cascade those AND gates. Right? Here I have INC ANDed with B0, and all I need to do is take that and now include B1 for B2, and for B3 I just need to throw in B2. So those AND gates have now been distributed. Right? Okay, so now they're all 2-input AND gates. I solved my problem, right? 64-bit? No? Yes?
And they all look the same, so you can make them modules.
Yeah, so if I make a 64-bit counter, this will work really well, right? You guys already don't trust me. Yes? What's the problem?
There would still be like a 64-bit AND gate for TC.
Okay, that's true. Okay. But otherwise it would work fine? What's the problem with this? I don't have a huge AND gate anymore, but I have some other problem. Well, TC is still massive, right? Yes?
Maybe a shot in the dark here, but if it takes a little bit of time for each AND gate to process,
Oh, it does.
receiving its input and outputting it,
Mhm.
then it'll take the added time of every AND gate instead of triggering
I have a long path here, right?
simultaneously.
So in the previous slide, I had shorter paths, right? Everything went just through one AND gate and an XOR. Okay, of course, these AND gates were getting bigger and bigger. But here, the AND gates are all the same size. They're 2-input AND gates, but now they're form a linear path, and that's going to delay it. Right? I'm going to have a path of 64 AND gates in a row in my 64-bit counter. So that's not good. Okay, so we traded one extreme for the other. Okay, we now have small gates but a long path. Okay, so there are lots of different ways of building counters. There's a whole conference on arithmetic that involves making arithmetic precise and fast, and circuits that compute it. One concept that I'm sure you're familiar is breaking things down into trees. Right? You do this with linked lists. You don't have everything flat for linear search, and you don't have long lists either. You find a happy medium. And that's what we can do with counters. We can break them down into smaller counters. So here, I'm using my 4-bit counter 4 times to build a 16-bit counter. Okay. Yes?
Where would the clock enable and the reset play for each?
I don't have a clock. Here I just have an ink. You can think of the ink as a count enable, if you like. There is a clock. Each one of these has a clock, right? And the clock goes only to the flip-flops clocks. Okay. So this counter, the one with the least significant bits, will count as normal. This counter only counts when this first one is at 15. So when you're at 15, TC will be high. If ink is high, then this counter will count. Along comes the clock edge. This counter goes from 0 to 1. This one goes from 15 to 0. And you're at 16, right? Which is where you want to be. Okay, at the next clock edge, assuming ink is high, TC will be low, so this one isn't going to count anymore. This one will just sit at 1, and this one will go from 0 to 1, and you'll be at 17. Okay, and you'll go all the way up to 31, and at 31, TC will be high. So this one will go from 1 to 2. This one will go from 15 to 0, and you'll be at 32. Okay, so we can build bigger counters this way. And now I only have a path of 4 AND gates.
And only 4 to the final TC.
Right. So inside each one of these counters is a 4-input AND gate. So basically I have a tree. Right? What we've done is we've taken the 16 bits, broken them up into groups of 4, and then each one feeds their output to the final TC. Okay, and we could keep doing this. We could take our 16-bit binary counter, put 4 of them together, hook them up like this. Okay, and then I would have only 3 levels of 4-input AND gates. Okay, so there are a lot of trade-offs. Where exactly the optimum, of course, depends on exactly how fast your gates are versus your wiring. Okay, so for this one, the third group of 4, I need the TCs from the previous 2. Okay, any questions on this? Does this seem easy? Okay. All right. So let's count down. Okay. So if I start at 0 and count down, I'm going to go to 15, right? and then 14, 13, and then we get to 0 and we blast off. No, okay, 15, 14. All right, so when does a bit change? Well, in this case, B0 changes every time. So that's the same. But now bit 1 will change whenever bit 0 is 0. Because now what's happening is you're borrowing. When you subtract, if you change if you're being borrowed from. Okay, so when I'm at 14 and I subtract 1, I then need to go back to 0. Okay, and if I'm 0 and I'm subtracted from, I'm going to go to 1. So it's just the opposite, right? Bit I will change. It'll go from 1 to 0 if I end up borrowing from that position, which means all the previous ones were 0. All of the previous bits were 0. If I subtract 1, in order for this bit to change, I have to borrow all the way. The only way that happens is if all of these are 0. Okay, and that works whether or not BI is 0 or 1. So we get the similar equation that looks like this. Bit I will change if we want to subtract, and all the bits to the right are 0. Yes?
Wait, so do we need like really new circuitry from the bottom up to swap between incrementing and decrementing? 'Cause
They're not the same.
why isn't it just the inversion again? Because that if you swap all the zeros and 1 in the chart that we just saw, like from
No, it's not the complement. No, this is an and of the knots, it's not De Morgan's law.
So the n comes before, the n comes after the knotting, not before the knotting. So what you were doing was knotting after the ands, but this has the knot before the ands.
All right, let's go on.
Turns it into an or.
It's not the same. You'll have to consider. Okay, all right. Any questions on this? So now you know how to decrement and increment. So the counter that you're doing in the lab is a lot fancier. It has a clock, as usual, right? And it has a count enable, and it has an up-down, right? And also a load. Okay, you're gonna have two different TCs. You're gonna have a TC going up. So this is the TC that we had, that was the AND of all the bits, and that's when the counter's full. When you're counting down, you need to know when you're about to go from 0 to 15 or 0 to 31. So this is the down version, or DTC, also known as 0. Basically, it tells you when the counter's at 0, so that if you count down, you know that you're going to need to you're rolling over, or you're rolling under, if you like. Okay. So you're going to need to add circuitry, additional circuitry to the flip-flops, because if you look at one of these flip-flops, say that's holding bit I, right? So we have our flip-flop here. Well, so we need to choose Okay. I can't seem to draw today. Okay, that's better. When the load is high, you're going to want to choose the appropriate bit. So this is BI. So again, when your load signal is high on the clock edge, you're going to load the value you're provided, right? So this is a loadable counter, which means you can set it to whatever value you want. If you want to start your count at 11, you can load 11 into it. Okay, but this only happens on a clock edge as usual. Okay, then if you're not loading, if load is 0, what gets loaded in here? Well, this is, of course, going to depend on up, down, and CE. Right? The increment that we were using is basically CE, all right, ended with up, down. I'll use Verilog since I made a point of that. And the decrement would be CE and not up, down. Right? If this is 1 and CE is 1, then on the clock you count up. But if this is 0 and CE is 1, then on the clock you count down. Okay, so this is the logic cloud. Okay. All right. Any questions on that? So we're leaving some of this to you. We're not telling. Yes.
Originally, I was thinking of making a multiplexer between incrementation and decrementation.
You could do that.
But you could do this as well.
There are lots of different ways of doing this. There's not just one solution.
Okay.
There are many design approaches to this. Yes.
Are we going to get to loading today? Because that's one I've really been struggling with.
Loading.
Yeah.
Didn't I just do that for you?
Oh, I thought. Okay, never mind.
Right. So basically, this is saying when load is high, ignore the cloud, and just put this value in.
Right. Okay. That makes sense.
Okay. If load is low, then this is going to behave as.
I misread LD at the bottom. I thought. Yeah. I got you.
Okay. All right. Yes.
And just one more thing. So we would use this design for each flip-flop, and should we also follow the design for the counter?
Yeah, so you're asked to make a 5-bit counter. So make a 5-bit counter and then assemble 3 of them to make the 15. Right? So you're going to have to feed the values from the previous one. And that means that you're going to have to figure out what increment and decrement is in terms of the UTC and DTC of the previous ones. Right? Because you don't want the second one. We don't want the second one counting all the time. We only want to count up if this one is at TC. So, or this one should count up if this one is at UTC. This one should count down if this one is at DTC and you're told to count down. Okay. But start by just making a 5-bit one. Yes? Any questions on this?
Sorry, the angle makes it difficult for me to read the diagram on the left. That's my fault for sitting here. But is that the memory? Is that the flip-flop, the D?
This is the flip-flop.
Something. So the one input for the multiplexer
this is, okay, so your
Ask again. I know you already said it.
your 5-bit counter will actually have a 5-bit value
Yes.
to load,
Yes.
right? I'm only showing you 1 bit here.
Okay.
So this is one flip-flop. It holds, say, bit I.
Yeah.
So you're going to want to pull out bit I of D in. That's the one that's going to be loaded into this flip-flop.
And is that itself pulled from the same flip-flop?
No, D in is an external input, right?
Okay.
Your your counter has a clock. It has a count enable. It has a direction, up, down. It has a load control, which has priority. The load overrides the count enable. Okay. What it loads is determined by a 4th input, which is a bus. Okay, you have to tell it what to load. It's not going to. Okay. Now this is a case where if you were to set the load to 0, you were to hard code the load to 0, connect 0 to it, you could just leave the D in unconnected, because even though it's unknown, it won't affect the flip-flop because it's never loaded. This MUX will never select this if this is 0. But yes.
So why do we have it?
Oh, well, you will want to use it. You will need to use it in later labs. You'll need to be able to load it.
Do we need it in this lab?
So in this lab, you're building it. This is a component that you will use over and over again.
But for this lab, we don't. That's not necessarily part of the point. It's just part of the construction of what.
Yeah, well, so the test bench that's in the lab actually will test the load, that the load works. It'll also test that you aren't that the load works even if you try to count at the same time.
So the objective of the lab is just to have this, rather than to solve a particular thing or have a particular outcome. It's just like, did the thing you make work?
Well, I guess most of the labs are, did the thing you make work, right?
Well, I mean, we had a calculator kind of.
Right. Well, this is a counter. It's a very important part. Okay, I want to do this simulation so that you can do your homework too. This is so we talked about how flip-flops behave, and so this is us behaving like flip-flops, and then figuring out. We're doing the job of the simulator here. Okay, and I think it's an important way to actually make sure you understand how the flip-flop operates. So you had timing diagrams for combinational circuits, and this is essentially a timing diagram now with flip-flops. The difference here is that we have clock edges. So there's a clock input. The dashed line is the clock edge. And then afterwards, there's a little dotted line. And the dotted line is when the flip-flop output changes. Because remember, the flip-flop output doesn't change right at the clock edge, a little bit after. Okay, and it gets really confusing if it looks like it changes right at the clock edge, because then you don't know what value to give it. Do you give it the value at the top or the bottom of the wave? When you're looking at the simulator in Vivado, it'll look like it changed right at the clock edge. But if you zoom in to the picosecond scale, you'll see that it's 1 picosecond after the clock edge. But usually you're not zoomed in that far, so it looks like it's right at the clock edge. And you just have to remember it's the value before the clock edge that it had at the clock edge. Okay. So, all right, so let's do this. My suggestion is always to do Q0 and Q1 first, and then come back and do the output Z. You don't have to do it this way, but it works pretty well. So what are Q0 and Q1 before the first clock edge?
Undefined.
Oh, wait, I wasn't supposed to do that yet. All right. So one thing you're going to want to do is get equations for the D flip-flops first. Okay, so we have a Q0 flip-flop, so we'll call its input D0, and we can get an equation for D0. Right, D0 is the AND of Q1 and X. And we can do the same for the other flip-flop. And D1 is Q0 ORed with X. Okay, and then the equation for Z is not Q1. All right. So again, what are the values of Q0 and Q1 before the first clock edge? Undefined. Okay, so we are told, in fact, that they are not initialized. So we have no idea if they start with 0 or 1. We have to put unknown there. Okay. So along comes the first clock edge. What will D0? What is D0 at the first clock edge? Undefined, right? Because Q1 is unknown and X is 1, and you AND 1 and unknown, that's unknown. So since D0 is unknown, that flip-flop is going to load an unknown value. What about D1 at the clock edge? What?
Should be 1.
It's 1, right? Because X is 1, and it's an OR. So we don't care what Q0 is. This is going to be 1. So Q1 is actually 1. So that Q1 flip-flop goes to 1. What about D0 at the next clock edge? Okay, X is 0 here. What will it'll be 0. Okay, what about D1? X is 0. Unknown. How many people think it's 0? How many people think it's 1? How many people don't know?
I'm still thinking.
Some people are still thinking. Okay. We need to know, we know X is 0, and we know Q naught is unknown. So we have unknown ORed with 0. Unknown. Okay, so you can pass an unknown value back and forth. Okay, what happens here? X is 1, Q1 is unknown. Well, but Q1 is unknown. Unknown. Okay, it passed its unknown back. Okay, what about Q1? 1. Okay, how about the next clock edge? This time, let's see, Q1 is 1 and X is 1. 1. Okay, Q0 is still unknown, but X is 1. 1. Okay. And now there are no more unknowns to be passed around. Q0, Q1 are known, and X is known, so you should never have any more unknowns. Okay, and now we just need to work out the values. So X is 0, which means that Q0 goes back. Q1 stays because Q0 is 1. Okay, X is 0, so this time Q0 stays 0, and this time Q1 goes low. X is 1, which is going to cause, which is not enough to make Q0 high because Q1 is low, but it does make Q1 go high, etc., etc. Okay? Any questions asked? You can do those step by step. Since they depend on each other, you've got to go in lockstep. You can't just do one without doing the other, because Q0 and Q1 depend on each other. Their next values depend on their current state. Z. All right, so let's do Z. What is Z in this time? Unknown? Completely unknown? Z depends on X and Q1 bar. It's not the output of a flip-flop directly. Yeah?
So if it's not the output of a flip-flop, it doesn't depend on the clock edge. So
Right.
if X falls to 0, it overends.
Right. So if X is 0, we know Z is 0, even though we don't know Q1. All right? So that's the thing, is we know Z whenever X is 0.
So now it's unknown.
Well, at the clock edge, it's unknown, yes.
But then in the next, once the next clock edge passes, we know Q1 and we know X, so we can just determine based off of.
Right, here we know Q1, and what is Q1? It's 1, so Q1 bar is 0, so we don't even care about X. Okay, and now we're back to the same issue. Q1 is unknown, but X is 0, so we know X, we know Z in the region where X is 0. But we don't know it here. Okay, and now from now on, we know it. And we get 3 cycles of zeros because Q1 is 1. And then wherever Q1 is 0, then we follow X. Okay. All right. I have one more of these, but I'm over time, so we'll have to do it on Wednesday. Yes?
If we're doing diagrams like this for our homework, do we need to include the delay?
So the assumption is the gate delays are as thin as your pencil. It's not that they don't exist, it's just that they're really small compared to the clock edge.
I'll enlarge them to show you.
Let me just